Hey everybody, this video lesson is going to discuss entropy, and it's also going to touch on the second law of thermodynamics. Now, what is entropy? Well, entropy is identified by capital S, specifically delta S, as in the change in entropy. Now, entropy, if you could sum it up in one word, is disorder, randomness. If something has a positive delta S, or a positive entropy, it is more disordered, meaning it's less ordered. If something has a negative delta S, then it's less disordered, or in other words, more ordered. Imagine your bedroom. Over time, your clothes end up on the floor, or your homework or your schoolwork just gets spread across the bed. Imagine your room becomes more disordered as time progresses. Things are just out of place, and it takes a lot of energy to put everything back in its place. Your room becoming more messy is an example of positive entropy, or more disordered. Now, one day you decide, I just can't take this mess anymore, and you're going to go back in, and you're going to clean your room. You're going to put everything back. You're going to throw away the dirty clothes into the hamper. You're going to hang up all the clean clothes that ended up on the floor. Maybe put away those clean clothes folded up in that laundry basket that your mom or dad set in your room and said, hey, you should put these away. You put away your books, organize your desk, maybe even vacuum the place. That's novel. Take those dirty dishes out from under the bed. You get the idea. You are becoming less disordered or more ordered. In this case, the entropy is negative. Now, the concept of entropy can apply to the system, which, if you remember back in our thermodynamics unit in Chapter 7, we talked about how the system is what you're observing, and the surroundings is everything that's not the system. Well, entropy can be applied to both the system and the surroundings. And if you add the system and the surroundings together, well, that's really everything that there is, possibly that can be. And so we call this the universe. This brings us to the second law of thermodynamics. The second law of thermodynamics says that the universe is tending to more disordered. In other words, if you factor in the entropy of the system and the entropy of the surroundings and add it together, it's going to tend to be more positive. In fact, it's never going to be negative. It could be zero, but it's never going to be negative. That is the second law of thermodynamics. Entropy of the universe is always becoming more disordered. So when your mom walks into your room and says, hey, clean up this room, it's a mess in here. You go, well, it's just entropy, Mom. It's just the way the universe tends it to be. And it actually makes sense when you think about it, because it takes a lot of work to keep your room clean. If you don't do any outside influence to keep your room clean, it will become disordered over time. Take it from me, who has 3 children. As soon as I clean up that living room, within 5 minutes, it's definitely more disordered. It's just a tendency of the universe to become more disordered. Now, if you take a look at the system and the surroundings, and specifically the entropy of the systems and the entropy of the surroundings, usually they're going to be opposites of one another. So if the system is becoming more disordered, the surroundings are becoming more ordered. So they have opposite signs. Now, if you add the entropy of the system to the entropy of the surroundings, and it equals 0, in other words, both of those numbers are the same magnitude but opposite signs, well then the entropy of the universe is 0. And we mentioned before, it can't be negative because it can't become more ordered. The universe is expanding, and so it's becoming more disordered. But if the system and the surroundings add together to equal 0, then what we have is a non-spontaneous situation. Think back to my last video lesson. We talked about spontaneous and non-spontaneous. Non-spontaneous is a situation where you have maybe a chemical reaction in dynamic equilibrium. The system and the surroundings are becoming ordered and disordered equally, but in opposite directions. And that is non-spontaneous and reversible. Now, if you add the entropy of the system and the entropy of the surroundings, and that number adds up to be greater than 0, well, the entropy of the universe then is greater than 0. If that's the case, then we, by definition of the second law of thermodynamics, have a spontaneous situation, because the universe is tending towards more disorder spontaneously. In this case, a synonym of spontaneous is irreversible. Now, the concept of order and disorder is a little bit more clear to you now at this point. But can you really quantify disorder? Well, heck yeah, you can. You can definitely quantify disorder. in order to quantify disorder, you have to factor in the enthalpy and the temperature. In fact, quantifying delta S is as simple as taking delta S is equal to delta H in kilojoules per mole, multiplied by the moles, divide by the temperature. Now, entropy is most often represented in joules per Kelvin. That's the unit of entropy, joules per Kelvin. Now, enthalpy is typically in kilojoules. So when you multiply the delta H times the number of moles, well, you eliminate the number of moles, and the moles cancel. And what you're left with is kilojoules per Kelvin, or joules per Kelvin. Like I mentioned, typically entropy is in joules per Kelvin, because if you measured it in kilojoules per Kelvin, it would be a really, 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 really small number. Well, how does this work? Well, let's take an example. In fact, this is right from the book. So if you read the book, you know what's about to happen. But let's take a piece of ice. That ice is the system. And if we take a look at the enthalpy needed to melt the ice, which we call the heat of fusion, and multiply it by the number of moles, and divide that by the temperature at which water fuses, then we can calculate the entropy of melting ice. So the heat of fusion, which is found in your textbook, is 6.01 kilojoules per mole. And let's, to keep our math easy, say we multiply it by 1 mole of water. So the ice cube is 1 mole, exactly 18.02 grams. So it's 1 mole of ice. And the temperature at which this happens is 273 Kelvin. Again, we got to make sure that the temperature is in Kelvin, just like we do for gas laws. So if we take 6.01 times 1 divided by 273, we get 0.0220 kilojoules per Kelvin, or kilojoules times Kelvin to the -1 power. This is typically how we identify the symbol or the units of entropy using negative exponents. But again, notice it's a really, really small number. So let's move the decimal point over 3 to the right to convert from kilojoules per Kelvin to joules per Kelvin, and you get 22.0 joules per Kelvin. That is the entropy, or the disorder, of melting ice. How about that? You just quantified disorder. Now, the heat absorbed by the system was lost by the surroundings. So if the heat of fusion of the ice was positive 6.01 kilojoules per mole, then the heat lost by the surroundings is negative 6.01 kilojoules per mole. Again, we're going to assume the surroundings has 1 mole of air. 1 mole of air is approximately 22.4 liters. That is a known value. It's the molar volume of a gas. So let's just say we have 1 mole of air surrounding that ice cube. Now, the air is held at a temperature that is room temperature. We'll call it 20 degrees Celsius, or 293 Kelvin. So what we got here is negative 6.01 times 1 divided by 293. Well, if we punch that into our calculator, we're going to get a negative 0.0205 kilojoules per Kelvin. Again, it's kind of a small number. Let's move the decimal point 3 to the right. It's negative 20.5 joules per Kelvin. Now you can see by comparing the two numbers that the ice is positive 22 and the surroundings, the air, is negative 20.5. So let's add those together to figure out the entropy of the universe. In this case, if I take 22 plus a negative 20.5, I get 1.5 joules per Kelvin. And that is a positive number, which is good because it can't be negative. We talked about this on the last slide. You can't have a negative entropy of the universe. It can be 0 or it can be positive. And in this case, since the ice is melting, it's positive, 1.5 joules per Kelvin. Now, very rarely, or in only specific circumstances, would you be expected to calculate the entropy of a system surrounding or entropy of the universe situation. But usually, you'll just be simply asked to tell me the sign, or tell whoever's asking, the sign of the entropy. In other words, is what's happening becoming more disordered, meaning positive entropy, or less disordered, negative entropy? And there are 3 situations that I want to talk about that would suggest an increasing delta S. The first is a change in state of matter. Changing in state of matter to a more disordered state of matter is always a positive delta S. So solid is the most ordered. So going from solid to liquid, that's positive delta S. Or going from liquid to gas is positive delta S. Or even solid to gas, which is known as sublimation. These all would be considered clues that entropy is increasing. Now, the second situation that I want to talk about is if you would observe a chemical reaction and you notice that the pressure goes up due to a gas being produced. So what you do is you look at the chemical reaction and you pay close attention to the moles of gas. And if there's more moles of gas as product than moles of gas as reactant, then that is a clue that there is an increase in entropy. So simply just account for the moles of gas on either side of the reaction. And if there's more products than reactants, then it's positive. And if it's more reactants than products, then it's negative. And if they're equal, then you can't make a judgment either way, whether or not entropy is increasing or decreasing, simply based on what you see. Finally, the third situation is anytime you take a solid and dissolve it in an aqueous solution or any solvent, dissolving is always a positive entropy. Because you're taking a solid substance and breaking it up into its small ions, it's becoming more disordered. And that should make sense to you. So these three are clues that suggest increase in entropy. So with those three things that we talked about on the last slide, let's see if we can figure out the sign of the entropy in these four situations. Let's take a look at this first one. We've got water as a liquid turning to water as a gas. Now liquid is fairly ordered and gas is very disordered. And so we have an increase in entropy because we're going from a more ordered state of matter to a less ordered. Also, this applies to the second one in which we have more gas as product than we do as reactant. So this is a positive delta S. Next, we've got silver ions and chlorine ions turning into silver chloride solid. This is the opposite of dissolving. This is a precipitation because dissolving takes solid and turns to ions. A precipitation takes ions and turns to solid. So this is the opposite of dissolving. And if dissolving is positive delta S, well then precipitation must be a negative delta S. Next, in number 3, we've got 4 iron ions and 3 oxygen molecules. And we are turning it into 2 molecules of Fe2O3 solid. Now, we're not changing state of matter, and we're not dissolving, but we are factoring in number 2 from before, which is the moles of gas. Now I see 3 moles of gas on the left and no moles of gas on the right. Now since we have more moles of gas as reactants and less moles of gas as products, then this must be becoming more ordered or have a negative entropy. Finally, the fourth example. We have N2 gas and O2 gas giving us 2NO gas. And we're not changing state of matter. We are not dissolving. And so let's take a look at the pressures or the moles of the gas on each side. And as you can see, I have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So in this case, I can't make a judgment either way. And so I'll have to say undecided at this point. Well, that takes care of this video lesson on entropy. Thanks for watching.